Imagine you've just finished building a giant jigsaw puzzle. You step back to admire your work, but instead of sitting quietly on the table, the pieces start sliding, bumping into each other and cracking apart. You are actually living on a puzzle like that right now. It's called planet Earth. Every single day, the ground beneath your feet is shifting. Most of the time, the movement is a tiny, invisible nudge, but occasionally the Earth goes into a full-on dance. We call that an earthquake. We can find the cause of these rumbles by looking at the specific way our planet is put together. The Earth's crust is divided into 20 slabs of rock called tectonic plates. Beneath them is a hot, semi-melted rock layer. As this gooey layer moves, the floating plates drift with it. They travel incredibly slowly, about the speed your fingernails grow. Since these plates are always moving, their edges eventually scrape past or slam into one another. We call these jagged meeting points fault lines. Since the plates are constantly crowding each other, these borders are where most geological events occur. How does that slow, steady crawl turn into a violent earthquake? Think about a thick rubber band. If you pull it further, it resists, building up tension until it snaps back and stings your fingers. This is how quakes work. Jagged tectonic plates try sliding past each other, but lock together. Deeper forces keep pushing, causing solid rock to bend and build extreme pressure. Eventually, the rock breaks. It snaps forward, releasing centuries of stored energy instantly. These quakes serve as the Earth's release valve for geological stress. The exact spot deep underground where that rock snaps is called the hypocenter. The spot on the surface directly above that break is the epicenter. That energy travels through the ground in seismic waves, moving through the Earth like ripples spreading across a pond. When those waves reach the surface, they force the solid ground to roll, which can tear apart asphalt roads and knock over utility poles. This energy is strong enough to buckle city streets and bend solid steel tracks instantly. If we understand the physics, why can't we predict the exact date and time of the next quake? We can map out high-risk zones, like the Ring of Fire, but rocks deep underground do not provide warning signs before they snap. Scientists use seismometers to catch the absolute first vibrations as a quake begins. These machines provide an early warning of a few seconds or a minute, but they cannot forecast a break days in advance. Because we cannot stop the plates from moving, we have adapted our engineering instead. Modern engineers now design buildings with flexible frames. These structures sway with the seismic waves rather than snapping under the pressure. For us, the best preparation is simple. If the ground starts to roll, remember, drop, cover, and hold on. These rumbles are just part of living on a moving puzzle piece. Have you ever felt the ground shake? Tell us about it in the comments.